In the last class, we were discussing the resolving power of telescopes. Let me resume the discussion where we had left it. So, I had told you that telescopes. So, here I show you the Hubble Space Telescope. It has an aperture of diameter 2.4 meters. This shows you the aperture. This shows you the giant meter wave radio telescope. This has an aperture of diameter 45 meters. This works at radio wavelengths. Now, the point was that if you use such a telescope to image a star, which is a point source, star being located far away is a point source. So, if you use the telescope to image a star, the image is the diffraction pattern of the aperture of the telescope. So, assuming that the telescope has a circular aperture, I had told you that the diffraction pattern is going to look like this. There is going to be a central bright spot. The radius of the central bright spot is lambda by d, 1.22 lambda by d. So, I had told you that a star is going to produce a diffraction pattern. The radius of the central bright spot is going to be 1.22 lambda by d in radians, and then we are going to have set of dark and bright rings around it. And the question which we were addressing is, how close can two stars be distinguished? So, there are two stars in the sky. If the two stars are very close together, their diffraction patterns would overlap, and I would not be able to make out that I am actually seeing the diffraction pattern of two stars, not one. Whereas, if the stars were far apart, the diffraction patterns would be distinct, and I could be able to make out that there are two stars. So, the question that we were trying to address is, how close can the stars be, so that what is the closest, the smallest angular separation between the stars at which we could distinguish and say that there really are two stars. There is a criteria which has been given for this purpose. The criteria was proposed by Lord Raleigh. So, it is called the Raleigh's resolution criteria for resolving two stars or two such images. So, the criteria is as follows. The blue curve over here shows you the diffraction pattern, that the intensity pattern that would be produced by one of the stars. It has a maxima at theta equal to 0, let us say. Now, we have another star at a different angle. So, it would produce its own diffraction pattern, which is the red curve showed over here. The two diffraction patterns would be displaced by an amount corresponding to the angular separation of the star. And what Lord Raleigh proposed was that we shall be able to distinguish, to resolve these two diffraction patterns. We shall be able to say that there are actually two different sources which are producing two different diffraction patterns, if the maxima of one of them is at least coincides with the minima of the other one. So, if the maxima of this coincides with the minima of this is the smallest angular separation at which we shall be able to distinguish, we shall be able to resolve the two sources. This is Lord Raleigh's criteria. So, it is called the Raleigh criteria. If the two stars are so close that this diffraction pattern has a peak somewhere here, then we will not be able to distinguish them. The peak of one has to coincide at least with the minima of the other. So, you can just resolve them when the peak of one coincides with the minimum of the other. If this peak were even further out, you could easily resolve them. The place, this angular separation where you can just resolve them is when the peak of one coincides with the minima of the other. And we have learnt that this for a circular aperture, the minima is 1.22 lambda by d. This angle away from the maxima. So, what we see here is that for a circular aperture, you would be able to distinguish two stars, the smallest angle at which you would angular separation at which you would be able to make out that there are two stars. This is given by 1.22 lambda by d, and this is what is called the angular resolution of a telescope. So, for a circular telescope with a circular aperture, the angular resolution is 1.22 lambda by d. This is the smallest angular separation at which I can distinguish two objects. If the two objects, the two stars were at an angular separation which is smaller than this, I would not be able to make out the fact that there are actually two and not one source. Whereas, if the angular separation is more than this or equal to this, I would be able to make out that there are actually two sources and not one. So, this is what is referred to as the angular resolution. So, for all optical instruments, there is always a finite angular resolution, and the angular resolution of optical instruments is set by diffraction, is decided by the diffraction, and it is typically of the order of lambda by d, where lambda is the wavelength of the wave that we are using. So, if it is optical, it could be 0.5 micron. If you are working in radio, it could be meters or millimeters or centimeters, and d is the size of the aperture of your instrument. So, let us calculate a few examples of this. So, let us go back to our to the two telescopes which we had discussed. So, let us first calculate the angular resolution for the Hubble Space Telescope. So, the angular resolution for any optical instrument is of the order of lambda by d, and in the optical, so let us assume that we are using the Hubble telescope to make an optical image. So, optical wavelength is of the order of 0.5 micrometers, and the diameter of the Hubble Space Telescope is 2.4 meters. This is approximately equal to 2 into 10 to the power minus 7 radians. So, the angle, with the Hubble Space Telescope, I would be able to distinguish, I would be able to resolve two sources if the angular separation of these two sources were equal to or more than 2 into 10 to the power minus 7 radians. If the angular separation was less than this, I would not be able to resolve the two sources. It is convenient and customary to talk about angles in terms of degrees, and each degree, if the angle is smaller than a degree, then each degree is divided into 1 arc minute, into 60 arc minutes. If it is even smaller than 1 arc minute, then each arc minute is again further subdivided into 60 arc seconds. So, let us just estimate what the value of this angular separation which we have calculated. This is the angular resolution of the Hubble Space Telescope. Let us estimate this in degrees, minutes or arc seconds, whichever is appropriate. So, to convert this into degrees, what we have to do is multiply it by 2 into 10 to the power minus 7 into 180 divided by pi. You can see that this number is much less than 1, and then we multiply it by 60 to get into arc minutes, and then into 60 to get it into arc seconds, and this, if you do the multiplication, comes out to be 0.04 arc seconds. So, the angular resolution of the Hubble Space Telescope is around 0.04 arc seconds if you use this lambda by d. So, the diffraction limit is 0.04 arc seconds. What is the angular resolution of the eye, for example, right? So, you could estimate this, take lambda by d for the eye. The pupil of the eye is the aperture that you which is there in the eye, and lambda is the wavelength of light. The angular resolution of the eye is of the order of arc minutes. It could vary from individual to individual, but it is of the order of arc minutes. So, you see that this the Hubble Space Telescope indeed has a very a high angular resolution, it is of the order of 0.04 arc seconds. Now, the question may arise in your mind, why is it necessary to send a telescope into space? Why not put a 2.4 meter telescope on the surface of the earth? You would have the same angular resolution. Well, there is a problem here. The earth's atmosphere is a refracting medium, and this refracting medium is actually changing with time. So, as a consequence of this, if I were to make an image of a star, at one instant of time the image of the star would appear somewhere here. At the next instant of time, the refractive index of the atmosphere would have changed and causing the image to move around. So, the image would be somewhere shifted, and finally, the image which you get would actually be quite a bit larger than that which is so the bright spot which you get corresponding to a star would be significantly larger than the bright spot which predicted by diffraction, and the size of this bright spot which you get when you do optical observations from inside the Earth's atmosphere would be decided more by the Earth's atmosphere and less by the diffraction, and typically you could achieve 1 arc second resolution from a good observing site. So, if you want to achieve angular resolutions below 1 arc second like 0.04 for the Hubble Space Telescope, you have to send your telescope outside the Earth's atmosphere. Let us now make another estimate. We have seen that the giant meter wave radio telescope has a diameter of 45 meters. And it works in the meter wavelength. So, let us assume that lambda is 1 meter and make an estimate of the angular resolution of a single dish of the giant meter wave radio telescope. This figure lambda by d now comes out to be 1, and I can take this to be approximately 50 meters. So, 1 divided by 50 is 2 divided by 100. So, this is equal to 0.02. 0.02 radians, and to convert this into degrees, minutes or arc seconds, whichever is appropriate, we can just work with 2 divided by 100 into pi I can take to be 3.14 divided by into 180 divided by 3.14. Let me take this to be 3 to just get a rough number. So, this is going to be of the order of 1.2 degrees. So, you see that with a single giant meter wave radio telescope, with a single telescope of diameter 45 meters, I get an angular resolution of only 1.2 degrees. This is a very poor angular resolution. The sun or the moon subtend half a degree. So, if the moon and the sun were close together, the giant meter wave radio telescope would not be able to say that there are actually 2 objects, not 1, because the angular resolution of the giant meter wave radio telescope, of a single dish of the giant meter wave radio telescope, is 1.2 degrees. So, I think the problem is clear to you. At large wavelengths, for example radio wavelengths, it is very difficult to achieve angular resolutions which are comparable to the optical. In the optical you can go up to arc seconds, whereas in radio, if you wish to achieve an angular resolution of 1 arc second, you would have to, let us just estimate this. So, if you want to achieve the kind of resolution, let us say which you achieve with the HST, you had angular resolution of 2 into 10 to the power minus 7. So, if you wish to achieve this kind of a resolution, you should have an antenna of diameter 2 into 10 to the power 7 meters, 20 million meters, which is not possible. You cannot make a single dish of 20 million meters. The giant meter wave radio telescope, so at lambda equal to 1, if you are working at 1 meter, you will have to build a telescope of diameter 2 into 10 to the power 7 meters if you want to achieve a angular resolution comparable to the HST. Obviously, this is not practical. So, the question is, how do you achieve high angular resolution at low wavelengths, large wavelengths or low frequencies, right? Optical frequencies have small wavelength, lambda by d is small, even for a modest size aperture like a few meters. In radio, the wavelength is large, so lambda by d is going to be a large number. If you want to achieve a small lambda by d comparable to optical, you will have to build a really enormous radio telescope, which is not practical. So, there is a technique called aperture synthesis, which I will not discuss. So, in the GMRT, for example, you do not use one antenna, you have an array of antennas. There are actually 30 antennas distributed in a Y-shaped configuration like this. The length of each arm over here is 14 meters. So, by using these few antennas, you are actually able to achieve the angular resolution as if you had a single telescope of this size, telescope which is this big. So, it is as if you had a single telescope of diameter around 25 kilometers. Okay. So, there is a technique called aperture synthesis, which allows you to achieve the angular resolution as if you had a telescope whose diameter was so big. It is not practical to build one telescope of such a large diameter, but there is a technique called aperture synthesis, which allows you to put together many small telescopes spread out over this and recover the resolution that you would achieve if you had a single dish of this size. It is called aperture synthesis. It is a very interesting technique. We shall not go into this. The bottom line of this discussion, let me just recollect the bottom line of this discussion. The bottom line of this discussion is that there is a fundamental restriction on the angular resolution of any optical instrument. This fundamental restriction comes because light or any kind of electromagnetic radiation, it is a wave. As a consequence of this, the image of a point source is not going to be a spot, it is going to have a finite size, and this imposes the angular the restriction that I cannot distinguish two sources. I will not be able to resolve two sources if they subtend an angle which is smaller than this. This is the resolving the angular resolution of any optical instrument. It is a fundamental restriction that comes from the wave nature of light. Let me now move ahead. Let me now take up something else. Let me okay. So, now we will have a quick switch in the topic of discussion. We are still going to continue discussing diffraction, but we are going to take up another topic for discussion. So, the topic which we are going to shift over to, let me introduce it. So, the problem that we are discussing now is as follows. We have a chain of oscillators. You can think of each arranged like this. Each circle over here is an oscillator. Each oscillator is emitting radiation. So, you can think of each of these circles as being a dipole oscillator, which we have discussed, which emits radiation. So, if you send an oscillating current in a dipole, it emits radiation. So, you can think of each of these circles as a dipole antenna, which is emitting radiation. There are n such dipoles. We have labeled them 0, 1, 2, 3, 4, 5, 6 all the way up to n minus 1. So, there are n such dipoles arranged in a linear chain as shown over here. The separation between two of the oscillators is a distance d. The oscillators are all oscillating with the same frequency and same phase. So, they all emit the same radiation of the same frequency and same phase. The question that we are interested in is, what is the radiation that will be received by a distant observer at an angle theta? So, in this direction, what is the radiation that will be received by a distant observer at an angle theta. So, a distant observer is going to receive the sum of the radiation from each of these oscillators. So, if we use E0, so I am going to use E0 to denote the radiation that is going to be received from the 0th oscillator, and then I am going to call the radiation that will be received from the first oscillator E1, and similarly the radiation that will be received from the second oscillator is going to be E2. So, the total radiation that is going to be received by a distant observer at an angle theta is going to, or at any other angle for that matter, is going to be the sum of all of these. So, it is going to be E1 plus E2 plus E0, sorry, this should plus E0 plus E1 plus E2 all the way up to E n minus 1. So, let me remind you again what we wish to calculate. There is a distant observer. The distant observer is going to receive the superposition of the radiation from all of these oscillators, and this is going to be E0 plus E1 plus E2 all the way to En plus 1, En minus 1. Now, each of these oscillator is oscillating at the same phase. So, they are emitting the radiation at the same phase, but the radiation will not be received at the same phase. This is because there is a path difference between the radiations from any two oscillators. So, let us look at E0 and E1. The radiation from E0 has to travel a slightly longer distance than the radiation from E1. So, the path difference is this bit over here, the path difference is the bit over here, and this will introduce a phase difference. So, the path difference between E0 and E1, the radiation from E0 and the radiation from E1 is d sin theta, and this will introduce a phase difference 2 pi by lambda d sin theta, and this phase difference I am going to call 2 alpha. So, what we can say is that E1 is going to be E0 e to the power I, it is going to come with a phase difference of 2 alpha e to the power I 2 alpha, right. And similarly, E1, E2 is going to be, so let me write it down here. So, the radiation from E0, from the 0th oscillator we are calling E0, the radiation from the first oscillator E1 is going to be e to the power I 2 alpha into E0. The radiation from the second oscillator has an extra phase of 2 alpha with respect to E1. So, there is an extra phase of e to the power I 4 alpha with respect to E0, and the nth oscillator is going to be at a phase difference e to the power I n alpha with respect to E0, where alpha 2 alpha is 2 pi by lambda d sin theta, right. So, the basic point over here is that a distant observer is going to receive the radiation from these different oscillators with a phase difference. So, there is going to be a phase difference between the radiation from the 0th oscillator and the first oscillator. There will be a phase difference between the radiation from the first oscillator and the second oscillator. So, the radiation from all of these oscillators are going to arrive at different phases. This phase difference is because of the path difference. The path from the different oscillators to the observer are not the same, they are different. So, when I combine all of these, I have to put in this phase. So, the resultant radiation that will be received by a distant observer is going to be the sum of all of these, and this sum we can write as n going from 0 to n minus 1. There are n of these oscillators, e to the power I 2 alpha to the power of n into E 0. Right, and this, so this is just a restatement of this. So, I have added up E 0, E 1, E 2, E 3. This is going to contribute e to the power I 2 alpha times E 0. This is going to contribute e to the power I 2 alpha square, I 2 alpha to the power n E 0, which is what I have done over here. I have written down the sum. Now, this is a geometrical progression. I can take the E 0 outside, and this is a geometrical progression. If I sum this geometrical progression, what I have is E 0 into the ratio of two consecutive terms to the power of n, n being the number of terms. So, the ratio of two consecutive terms here is e to the power I 2 alpha, this to the power n minus 1 divided by the ratio I 2 alpha minus 1. Right, and we want to now, this is the resultant radiation that will be received by the observer. We want to do, we have summed up all the contribution from all of the oscillators. We want to simplify this expression a little bit, and this can be done by writing it as E 0. I will take e to the power I n alpha common over here. So, I have e to the power I n alpha common, and then what I have over here is e to the power I n alpha minus e to the power I minus I n alpha divided by, in the denominator I will take e to the power I alpha common. So, this I will take e to the power I alpha common. So, in the denominator I will have e to the power I alpha minus e to the power minus I alpha, and you can see that this is going to be sine n alpha, this is going to be sine alpha. So, the resultant electric field, the resultant radiation received by a distant observer is going to be E 0 e to the power I n minus 1 alpha into sine n alpha divided by sine alpha. The sine n alpha comes from this, the sine alpha comes from this difference, there will be factors of 2 and I which will cancel out from both of these, and e to the power I n minus alpha is this ratio over here. Now, we want to calculate the intensity. So, the intensity, as we have seen many a times, is half E into E star, and this can be written as, so I have to multiply this with its complex conjugate. If I multiply it with its complex conjugate, I will get E naught square. Multiplying this with its complex conjugate gives 1, and I will have sine square and sine square here. So, I can write it as I naught sine square n alpha divided by sine alpha, sine square alpha. So, this is the intensity pattern that will be produced by this chain of oscillators. So, this is the intensity pattern that will be observed by a distant observer produced by this chain of oscillators. Let me also write down here what alpha is. So, alpha is pi d sin theta by lambda. So, this is the intensity pattern. Now, let us analyze for a few minutes, let us analyze what this intensity pattern looks like. To start with, let us consider the point where theta is equal to 0. What is going to be the value of the intensity where theta is equal to 0? Theta equal to 0 implies that alpha is also 0. So, this I can write this, I want to evaluate this at alpha equal to 0. So, I can write this, let me do it a little elaborately for you. I can write it as I naught sine square n alpha divided by n alpha square, this divided by sine square alpha divided by alpha square. I have to put a factor of n square here. So, this it should be clear is the same as this expression for the intensity. All that I have done is I have divided it by n square alpha square, divided this by alpha square, there is an extra factor of n square which I have to put over here. So, this is what I get. Now, if I take the limit of alpha going to 0, this ratio we know is 1, this ratio is also 1. So, we know that this is going to have a value I naught n square. So, what we have seen is that alpha going to 0, the denominator and the numerator both vanish, and we have the ratio of the both vanish, but the ratio is finite, it assumes a value n square, and this is the maximum value that the intensity is going to have. Now, if you increase alpha from 0, if you increase theta from 0, so the value of alpha is also going to increase, sin theta is going to increase, this is also going to increase, but this ratio is going to fall. But there will be a maxima again whenever the value of alpha disappears. So, the value of alpha is again going to disappear when sin theta vanishes. So, sin theta is going to vanish whenever it is when theta is a multiple of sorry it is not that this okay, this ratio you see when if alpha changes. So, at alpha equal to 0, this ratio is n square. Now, sin the denominator vanishes, the denominator as you can see is going to vanish whenever sin alpha is 0, and we know that sin alpha is 0. Okay, let me make this point clear. The intensity is going to have the maximum value whenever the denominator becomes 0. So, the intensity is going to have a maximum value whenever the denominator becomes 0. It should be clear. So, this happens whenever alpha is equal to either 0 or plus minus pi or plus minus 2 pi, etc. It is also clear that whenever the denominator is 0, the numerator is also 0. So, this ratio becomes n square, and these are the points where the intensity is maximum. So, the intensity is maximum whenever alpha is equal to plus minus pi, 2 pi, etc. The maximum value of the intensity is n square I naught. So, the maximum value of the intensity is I naught into n square, and there will be many of them whenever alpha is equal to 0 or plus minus pi or 2 pi, etc. Writing this out in terms of the angle theta, we see that the maximum is going to occur whenever d sin theta pi by lambda is equal to m pi, where m can be any integer 0, plus minus 1, 2, 3, etc. Or it tells us that d sin theta is equal to m lambda, where m can have values 0, plus minus 1, plus minus 2, plus minus 3, etc. Let me repeat this again. We are looking at the intensity that is going to be produced by the chain of oscillators, and we have derived and found that the intensity pattern is given by I is equal to I naught sine square n alpha divided by sine square alpha, where alpha is pi d sine theta by lambda. Let me just, to get things clear, let me remind you, theta is the angle at which the observer is located. So, this tells us how the intensity is going to vary if I change the angle theta in different directions. And what we find is that the intensity is going to have maximum value whenever the denominator becomes 0. Now, it is ensured that whenever the denominator becomes 0, the numerator is also 0, because the denominator becomes 0 whenever alpha is a multiple of pi. And if alpha is a multiple of pi, alpha 0 plus minus pi 2 pi etc. So, this is when the denominator vanishes. It is guaranteed that the numerator also vanishes, and this has a value n squared. These are the maximas of this intensity. So, there will be certain directions at which the intensity will be maxima. These directions, these values of theta correspond to alpha equal to 0 plus minus pi plus minus 2 pi etc. In these directions, the intensity is going to maximum, the maximum value is I naught n squared. So, to determine the direction where you are going to have the maxima, set alpha equal to this, which in terms of the angle theta now becomes d sine theta is equal to m lambda. So, for different integers m, I will have different solutions theta, or sine theta is equal to m lambda by d. So, if lambda by d is more than 1, if lambda by d is more than 1, you will have only one solution, m equal to 0, which is theta equal to 0. If lambda by d is less than 1, you can have more than one solution for different integers n, m, right. And these solutions correspond to these values of alpha, where the denominator and numerator both become 0. Now, let me plot this intensity pattern and show it to you as a function of alpha. So, if I plot the intensity pattern as a function of alpha, it looks like this. Whenever alpha is 0 or alpha is pi, 2 pi, minus pi, I have these maximas. The numerator and the denominator both vanish. Now, if let me just consider a situation where we are looking at alpha equal to 0. So, I am looking at this point and I increase alpha. If I increase alpha, the value of the intensity is going to fall and it is going to go to 0. The numerator, you see, look at the denominator first, not the numerator, look at the denominator first. The denominator starts from 0, it increases and then it becomes 0 again when alpha goes to pi. So, we are looking at alpha starting from the value 0, where we have a maxima in the intensity. As you increase alpha, the denominator increases and then it falls and again goes to 0 at pi. That is the other maxima over here. These maximas are called the primary maximas. These are called the primary maximas. So, we shall refer to these maximas as the primary maximas. And the primary maximas occur whenever the denominator becomes 0, which is alpha equal to 0, pi, etc. Now, let us look at the numerator. As alpha is increased, the numerator goes to 0 n minus 1 times between. So, alpha starts from alpha equal to 0 and then alpha goes to pi. the denominator has gone from one 0 to another. How many times does the numerator become 0 in between? It should be quite obvious that the numerator becomes 0 n minus 1 times in between. This is what you see over here. So, the blue curve shows you the intensity pattern. If I had 5 oscillators, and you can see that it becomes 0 once, twice, 3 times and 4 times in between the value 0 and pi, the numerator becomes 0 exactly 4 times. So, in general it is going to become 0 n minus 1 times in between 2 primary maximas, and between these zeros of the numerator there are going to be secondary maximas over here, here and here. So, between 2 primary maximas we will have n minus 1 minimas and we will have n minus 2 secondary maximas. So, as you can see here, there are two things. The secondary maximas have a much lesser intensity as compared to the primary maximas. The other point to note is, as I increase the number of oscillators, the number of zeros in between the 2 primary maximas increases. The number of zeros, not only does the number of zeros increase, but the intensity of the secondary maximas also goes down. You cannot see it here actually, you can only possibly see only the first one and you cannot see any of them. After that, also the width of the primary maxima decreases as you increase the number of oscillators. So, the primary maximas get sharper and sharper. Let us now estimate the width of the primary maxima. So, the primary maxima occurs whenever alpha is equal to a multiple of pi. So, let us say that it is equal to m pi. M is called the order of the maxima. So, m is the order of the primary maxima. So, we are looking at the mth order primary maxima. Alpha equal to 0 is the 0th order maxima, alpha equal to 1, alpha equal to pi is the first order maxima, alpha equal to 2 pi is the second order maxima. In this picture, this is the 0th order maxima, first order maxima, second order maxima, second order primary maxima. So, this is the value of alpha corresponding to the mth order primary maxima. Let me call it alpha m, and alpha m, alpha we know is pi d sine theta. So, the corresponding angle would be theta m. M equal to 0 corresponds to theta equal to 0. Let me just show you this, right. So, theta equal to 0 means that in this direction, theta equal to 0 is this direction. M equal to 1, theta would be larger. So, it would be somewhere possibly here. M equal to 2 would be even larger. So, higher order maximas occur at a larger angle. So, let us focus our attention on a particular order of the primary maxima. So, we have a particular order, mth order primary maxima. Now, as you increase theta away from that, so if you change theta away from theta m, the value of alpha is also going to increase. This is alpha. So, let us say that we have changed theta to theta m plus delta theta m, and alpha would have changed correspondingly pi d sine theta by lambda. This is going to be alpha m plus delta alpha m, and a change in alpha away from m pi means that the intensity is going to fall, and we want to estimate the width of this maxima. So, we should, with the question we ask is how much should we change theta so that the intensity falls to 0. So, we start from a maxima, the question is how much should we change theta away from the maxima so that the intensity falls to 0, or how much should we change alpha so that the intensity falls to 0. Now, at the maxima alpha is equal to m pi. So, let us look at the numerator of the expression for the intensity. The numerator of the expression for the intensity, so this is the expression for the intensity. The numerator for the expression for the intensity is this. Let us look at just the numerator term. The numerator term is sine square n alpha. So, to start with, we are at alpha m, where the numerator is 0, but the denominator is also 0, and then we increase alpha to alpha m plus delta alpha m, and ask the question how much should the increase be so that the intensity vanishes. And it is very clear that the change, so we have started from n alpha m is equal to m pi, and the change should be such that n alpha m plus delta alpha m should be m pi plus pi, right. We start from 1 0, but there the denominator is also 0, and then we increase alpha and ask the question when does the numerator become 0 again. That is the point which will correspond to this, where the intensity vanishes. So, this is the condition that the change in alpha should exactly the change in the numerator, this argument of the numerator should be exactly 1, should have increased by exactly pi. So, this basically tells us that delta alpha m or alpha plus delta alpha m should be equal to this, this is the condition, okay. And alpha m we know is already equal to m pi. So, this basically tells us that delta alpha m should be equal to pi by n, right, which you can see straight away from here also that there are n minus 1 zeros in between. So, delta alpha n should be pi, this is pi divided by the number of zeros, which is n, and the number of intervals in between, which is n, okay. And how much is delta alpha m? We can estimate that from here. So, delta alpha m, we can assume that delta theta, the change in theta is small. So, if the change in theta is small, we can expand this and we can write it as pi d by lambda. Sine theta plus delta theta can be written as sine theta m. Cos delta theta we can take to be 1, assuming that delta theta m is much less than 1. So, this plus cos theta m into delta theta m. This is equal to alpha m plus delta alpha m, and alpha m is exactly equal to this first term over here. So, this can be dropped. So, what we get is delta theta m is equal to delta alpha m, and delta alpha m for the numerator to vanish we have worked out should be pi into pi divided by n. So, the condition that we get is that this delta theta into, sorry, I can write it out like this, pi d cos theta m delta theta m by lambda is equal to pi by n, which gives us that delta theta m is equal to lambda by n d cos theta m. Okay. So, what we have worked out, let me just remind you what we have worked out. We have worked out the width of the maxima. So, when I have a chain of oscillators, what we see is that the intensity pattern will have maximas in different directions wherever this condition is satisfied, and as I change theta away from these directions where this condition is satisfied, the intensity is going to fall. And the question we ask is, what is the width of the intensity peak? And we have calculated the width of the intensity peak. So, the width of the mth order principal maxima is lambda by d n cos theta m. D is the distance between the oscillators. So, as I increase the distance between the oscillators, the primary maximas become sharper. If I increase the number of oscillators, the width of the primary maximum becomes sharper, it gets smaller. The primary maxima itself gets sharper. And if I look at this, for example, if I look at the 0th order maxima, the 0th order maxima occurs when theta is equal to 0 in this direction. If I look at the 0th order maxima, cos theta m is going to be 1. If I look at the first order maxima is going to occur at theta equal to sin inverse lambda by d. So, it is a larger value of theta. So, cos theta is going to be smaller. So, what we can say is that the 0th order maxima is the sharpest, the first order maxima is somewhat broader, the second order maxima is even more broader. Okay. So, what we have done till now is that we have considered the radiation that will be received by a distant observer from a linear chain of oscillators. Now, let me give you a problem and end the class in the next lecture. Okay, before giving you the problem, let me discuss one more thing and then I shall give you the problem. When we started our discussion of the linear chain of oscillators, we had assumed that all the oscillators are oscillating with exactly the same phase. Now, we will consider a situation where the oscillators themselves are oscillating with a phase difference. What we will assume is that there is a phase difference of 2 phi between any two successive oscillators. So, between oscillator 0 and oscillator 1 there is a phase difference of 2 phi. Between oscillator 1 and oscillator 2 there is a phase difference of 2 phi and so forth. The question is, how does the intensity pattern get modified because of this? If you look at the way we have derived the intensity pattern, what we have done is we have added up the contribution from all of these oscillators with phase differences, the phase difference arising solely due to the path difference, and this gives rise to a phase difference of 2 alpha. So, the path difference introduces an extra phase difference of 2 alpha, which occurs due to this path difference. Now, in this situation where the oscillators are themselves oscillating with an extra phase difference, what you have to do is throughout all the expressions you have to replace 2 alpha by 2 alpha plus 2 phi. Okay. That is all that has to be done in all these steps. So, for example, in the expression for the intensity, what you have to do is you have to replace alpha by alpha plus phi, where phi is now the phase difference between the oscillators themselves. Okay. And if you do this replacement, you will find that the condition for the maxima is what is given over here. So, we have now seen how to also handle the situation where the oscillators are not oscillating with the same phase, but there is a phase difference of phi between any two phi between any two consecutive oscillator. Let me now give you a small problem and I will end the lecture over here. So, the problem is as follows. Consider a linear chain, a chain of 100 dipole antennas. So, each each oscillator over there is a dipole antenna. So, in the picture which I had in this picture, each oscillator is a dipole antenna and we have 100 such oscillators. The distance d between two successive oscillators is 1 meter and all the oscillators are radiating at a frequency of 150 megahertz. So, all the oscillators are being fed with a signal with a current, oscillating current, which is oscillating at 150 megahertz, same phase. So, all the oscillators are dipole antennas are oscillating with the same phase. So, they are all radiating with the same phase. The question is, the first question is, in which direction do we have the intensity maxima? So, in which direction is the maximum intensity? The second question is, how many such maxima are there? We have seen that there could be more than one maxima. So, how many such maxima are there? Then, what is the width of the maxima? And finally, suppose we give, what happens if there is a phase difference of pi by 8 between the oscillators. So, suppose I give a phase difference of pi by 8 between any two oscillators. So, pi by 8 between this and this, pi by 8 between this and this. So, there is a phase difference of pi by 8 between each of these oscillators. So, what happens to this, all of these questions if I introduce an extra phase of pi by 8 between any two oscillators? So, we shall continue our discussion from here. We shall take up the solution of these problems and then discuss several implications of the various formulas that we have derived today.